Hello, hello, hello. Uh,
Good morning.
Good morning. Good
Good morning, Professor.
morning, guys. Good morning. Thank you. My weekend. I just saw. My weekend was good. Thank you very much. Thank you, Kimberly. Okay. Good morning, Wenyi. Good morning, Brian. Good morning, Kimberly. Good morning, Eileen. Good morning, Leah. Good morning, Abby. That is Aaron. Good morning, Justin. Good morning, Brian. Good morning, Rachel. Hello, Andre. Hello, Sabrina. Hello, Aaron. Now it is good morning, Brian. Thank you. Now it is. I'm very late here, and this is unexpected. I mean, unexpected by me. I just had class, so there's no reason I should be this late. Um, but I have to say that we seem to be in a very. I'm having a major internet problem in my right now, which is not only affecting me and this class, but other people. So I'm very sorry I'm late. I actually thought I had fixed this in the middle of my other class, and I thought everything was gonna be fine. And then we're hanging on so I'm not trying to be dramatic, but I'm actually right now doing this from a tether on my phone, and that is not helping the rest of my family who's trying to do things as well. So this may be well, oh, there's more people. Sorry. So sorry, I was actually quite looking forward to this class, and we do have things to do and stuff, but this may be very touch and go here, including the issue of whether I have a board. So I'm actually, so I think, yeah, I'm going to, so I apologize. I'm going to try to get two things like straight back to the material. So I may get a little bit lectury here and a little bit in my head, and I apologize because I also might have to hop. I don't want to get anybody's hopes up, but the class might end up ending early. And if I have to end on a dime, just you are the class, then yes, then my status report with your homework is still the same. I think we now it's on Wednesday, we'll start talking about the midterm exam. We won't do that today, but I think everybody is fine with the homework and keep on pressing on, blah, blah, blah. I'm just going to get straight. Okay. I'm going to get straight to physics now. Sorry. Hold on. Excuse me. These people coming, or are not people coming. Sorry. So bear with me for a minute while I try to get the board online. That's what I'm doing right now. And if there are questions at all, it will distract me. Right now, I'm going to focus for a second and try to fix this. But if there are any questions about where we are or anything, do feel free to put them in the chat. I will try to. I would be happy to know that I'm not just talking in space. But I'm going to need a moment. Tell me if this worked. That's a good sign. Okay, there's progress. I think something's happening. Okay, I apologize again for all of this and anybody who just joined. We started very late because I'm having issues, as always. But you should now, we should be rolling now with the board. Yeah, I think you can see the board. Yes. Okay, we are recording. Okay, okay. Okay. So here's what I think we have right now. Right, we have that, we're given that, physics tells us, Hooke's law tells us that, and we, as of last class, we conjecture right, this is our conjectured solution. We have a second order differential equation. We're looking, so it tells us something about the second derivative of x with respect to t, but we want x as a function of t. Our conjecture is that x is a cosine function of t, specifically one that has these two constants in it. This conjecture, we need to find out if it's right or wrong, number one. And number two, even if it is right, it's only meaningful if we have any idea what we mean by x naught, which we do, and omega. Like, we have to know what those constants are, otherwise this is not a complete solution. So where we left last time, we said is we're gonna differentiate. And in principle, you guys might have made, I mean, well, anyway, where we left last time is we're going to differentiate our conjecture in order, one, to find out if it's true, and two, if it is true, to find out anything we can about the constants. Okay, so and I guess this, yeah, I guess I did this last time, but so I should really say. Okay, so again, this is where we, like, I think this is right exactly where we left off last time. Oh, and this says verify. Okay, so yeah, and you might want in the background, if I'm going, try it yourself. Even if you've done 100 times, you might want to try to go a little faster than me. Like, I want you to, we want to take a derivative of this with respect to t, and then we want to do it again. Actually, maybe I should. All right, I'm going to turn it to you guys. I mean, if you think you know, you might want to put in the private chat if you want to give someone else a moment. I want to know the first derivative, and then I want to know the second derivative of this expression So I want dx dt, then I want d2x dt, and man, maybe we'll participate at however you want, but you can put it in the private chat, or you can say, public chat, or you could say it, but or no. I'm just sort of deliberately going to move a little slow just to give you, so we have this. But I think I am, oh, cool. I see something in it, cool. All right. Yes, I totally agree with something I see in the private chat. That's awesome. I think I want to make sure there a lot of people are with me here. Because, yeah, I mean, I know it was a week ago, but so everybody should take a moment. You want to take the derivative of that with respect to t, and then you want to do it again in order to see that we're getting anywhere or doing anything. I think I want to get a couple more either in the private chat or public before I go on. Oh, so what I'm asking everybody is, let's see, this is what I get for having an unstable internet state. So we do want, I don't know if I've lost everybody. I mean, oh, more people. Oh, cool. Okay, cool. Great. Now there's a couple of people. This is good. Now, I don't know if it's good or bad that hold on one second, I'm just gonna respond. So if some people are I'm just gonna arbitrarily wait till at least one more person, either in the private chat or public chat, gives me an answer. It's a little bit unfair on my part. You know what makes me a little suspicious? And it's perfect that what I've gotten so far in the private chat is perfect, and I'm totally impressed. And they win. I mean, they win in life. Oh, and here's another one. Great. The only thing that makes me slightly concerned is that the only things that are coming in the private chat are correct answers. So that means there's something, that means that there are people that, that's great. People that, I'm very impressed with the people that wrote in. I don't need to make this a private show, and they can quote, they can double dip this later. But all right, okay. So a few people have written in the private chat. I hope other people are following this though. Like, so I do agree. Like we have to do trigonometric derivative and chain rule. So I do agree that, oops, sorry, no, I don't. Something like this, actually, I'll, yeah. Actually, sorry. Even better to write it like this. Right, that's the first one. And then, so it's chain rule is what brings the omega out, so to speak. And the negative, well. Oh yeah, and maybe I did, maybe I'm gonna just assume this is sort of boring because we had done it before, not that it's so over, but yes, good. So some people, now what's my point? Our point, I guess we did say this last time, I'm sorry, maybe I'm dragging our feet here. But what this part here is super important because this, if we remember, right, that x naught cosine omega t thing is what we mean by x. I mean, that's what it says right here. So evidently, and I apologize, maybe if I already totally did this whole thing already, but it is very important and it's easy to get wrong. But what we seem to be saying is um, right. Oh, and I see, oh, cool, in the chat. I'm just looking, this is cool, something in the chat. Where is this? Nice. Hold on. Right. So subtlety is we were looking for some X such that this was true, such that we were looking for an X such that when you differentiate it twice, you get back itself times some constant times a negative sign. And of course, the cosine function sounds really good because that is exactly what happens to the cosine function. When you differentiate it twice, you get back itself times a negative sign, right? So that's a good start. And here we were saying we want to get back to ourself times some constant, a constant that we called k over m, right? But k over m is a constant. And remember, omega was a constant, and all we ever restricted about it was that it needed to be measured in radians per second. And that's all that needed to be true of it. So there's no reason it couldn't equal k over m. So what we seem to be saying is that, therefore, our solution is right. Oh, yeah, I'm sorry. I guess we did finish it. I guess I am being repetitive. I mean, this is really important, but yeah, I guess we did already do this part Wednesday. I apologize, but we are literally saying this if and only if by omega we mean, right, and we did conclude this on, if as long as those are two different names for the same constant, or yeah, as long as those are just two different constant names for the same number, then this all works. And there's no reason they can't be because omega wasn't restricted except by units. So as long as the units work out, then this is all fine. And this is how you solved for the last question on homework 1, I recall now. So now I'm going to go. What does this mean to us? Okay, it does mean like, really, what are we taking away from this? Well, for one thing, for sure, on the most primitive level, the most concrete or particular level, what we're taking away from this is our answer to question number 9 on homework 1, right? But what that, of course, is artificial. But what do I really mean by that? Well, okay, the first thing that we're taking from this is it is true as long as you have a mass on a spring, like you know the size of the mass and you know the stiffness of the spring, and you let it go, you release that mass from equilibrium. What we seem to be concluding here is that a mass will oscillate back and forth at some kind of constant rate, right? Like all the symmetry and everything of questions 1 through 8, if we put together, we're saying that if you put a mass on a spring and you extend it away from the equilibrium position and you let it go, it will oscillate. It'll go back and forth at a constant rate, that I'm going to call angular frequency here. And that rate seems to be entirely determined by the stiffness of the spring and the heaviness of the mass, like in this particular way, square root of k over m. A constant angular frequency of omega. What do I mean by that? Okay, angular frequency, omega. It's time for us to talk about it directly. I've been saying it originally emerged as just a placeholder. Omega, we just put there because we knew that some constant had to be at a certain place in our expression simply to make the units work out. Like the only thing we've known about omega to this point is its units. But as scientists, that means we know a lot. We know that omega measures radians per second. What the heck does that mean? Well, one way to look at it, of course, is if you picture a graph, if you picture a cosine graph, and if you picture that the x-axis or the independent axis is measured in seconds, and the y-axis is measured in sorry, I'm actually getting that. Well, yeah. Well, I mean, if you make a cosine graph, one way to picture radians per second is in some ways how many seconds it takes, how many humps or crests or troughs of that cosine graph you can count per number of seconds. That's one way to think about it. But oh, excuse me. Hold on one second. I'm sorry. Hold on one second. Yeah. Yes. Yeah. Yes. I'm coming. I hear you. I hear you. Yes. Sorry. Sorry. This is still here. Okay. You guys can still, you're, oh, wait, could anybody give me a sign that you're still?
We can hear
We
you.
can hear you.
Okay, thank you. All right, I know this is all very, all right, thank you. So the real question is, what do I mean by radians per second? Because, and here's the answer. A radian is fundamentally a fraction of a circle. A radian is a portion of a circle, a section of a circle. That is literally what a radian is, and it's well, here we go. Sorry. Yes. Yes. Okay. Okay. This may not, I may be fighting an uphill battle here. All right. I think this is not, sorry, this is not working. Um,
Okay, so that is one project. The other one is, anti-static.
all right, I'm gonna give this one last shot. All right, I'm gonna keep, as I say, I'm sorry, I may cut this at any moment, but I'm gonna try a little bit more here.
Hey, Dad.
Hey,
I have
Dude.
a cool game.
you do? Yes.
And it doesn't involve any going downstairs.
But is it about saying hello to this class that I'm in the middle of?
No.
Do you want to say hello to this class?
No.
Well, then you better do.
I will if you play my mini game.
I would love to play your mini game in
It
like 2
doesn't involve any internet. And it's very short. All you have to do is guess what's in my stomach, and if you win, you'll get a prize.
What's in your, I guess that what's in your stomach is an apple,
No.
an orangutan,
No.
an elephant,
No.
something that rhymes with fix.
Something that would actually fit in there. That's a candy.
You got a candy? Mom gave you, then I can't, even though you're sick, then you're very lucky. But it couldn't possibly, you wouldn't be lucky enough to have a Twix. That would be crazy.
Ha! You got it wrong. It was Twix.
Oh, no. Oh, all right. You're the winner of the mini game. Oh, that's awesome. All right. You totally enjoy that. And I'll be down in 10 minutes and then and then I won't get one. But I got to do
And then you'll fix the internet.
that. I will try very hard. Yes, that will be my mission.
And then you'll blame Nintendo
Yes. Yes, that's right.
for everything they do.
All right. Now I got. Okay.
And I can stay in.
Yes, you can stay. Yes. Okay.
Oh,
All right,
baby.
Wait. Okay.
Oh, baby.
Okay.
Behold my greatest invention, Dad. Oh yeah. Oh baby. Mama.
Back to this board in 1 second. If anybody needs. Okay. If I do nothing else today, and I probably will do nothing else, and if I do nothing else with my life on this planet, I will attempt to pass on the wisdom of what exactly a radian is to all of you lucky people. Like, I think this is the one thing I really feel the need to teach. What is a radian? A radian is a sixth of a circle. A radian is a sixth of a circle, approximately. It's not exactly a sixth. It's a little bit less than a sixth, because 2 pi is a little bit more than 6, right? Like pi is a little bit more than 3. All a radian is all an angle is a section of a circle. An angle is a fraction of a circle. That's what an angle is. Like a right angle, like no matter how long the lines are or short they always come together this way, a right angle, right? And whether you call it 90 degrees or you call it pi over 2 radians, whatever you call a right angle, what is it? It's a fourth of a circle, right? What's a 180-degree angle? Whatever you call it, it's half a circle. An angle is a section of a circle. That's what an angle is. And radian is just the most natural way to measure angles. It's just, radian is just a way of not introducing anything but what an angle is, which is the pure ratio of arc length to radius, right? That's what an angle is how much crust, what an angle is how much crust of pizza you get per size of pizza, if that makes any sense. So put another way, well, anyway, an angle is a section of a circle. A radian is that precise section for which the arc length of the section, the crust of the pizza slice, happens to be exactly equal to the radius of the slice. That, in fact, an even better way to put that, so, right? Okay. Oh, good. I'm glad. Okay, cool. Oh, I'm sorry. There's a lot in the chat I just missed. I'm sorry. Oh, right. That was what I used to do. Okay, thank you. Oh God, yes. Okay, well, thank you for your comments. Right. But yeah. Okay. Speaking of pizza, like, so, and what an angle is a section of a circle. And why I keep saying section of a circle, the whole thing of an angle is that it doesn't matter what size the circle is, right? Like you can recognize a half of a pizza no matter how big the radius of the pizza is. That's what we mean by angle. Like, in other words, you'll get twice as much crust as me if you have twice as much of a section of the same pizza, right? But of course, another way to cheat and get twice as much crust as me is to take the same slice, but out of a much bigger pizza. So just in order to like normalize all that, to just say, so that we don't compare apples to oranges, what an angle is it's like how much pizza crust you get, but assuming that you're all cutting from the same pizza slice, where the radius is the same, is 1. So another way to put what an actual radian is, is that amount of arc length. I mean, it's that angle for which S, the numerator arc length, equals R, right? Like, because like 5 over 5 is equal to 1, 6 over 6 is equal to 1, anything over itself equals 1. So when the arc length and the radius are exactly the same, that's the angle that we call 1 radian, right? 1 radian is approximately a sixth of a circle. It's like 1 over 2 pi of a circle. And another way to put it, if you really think about it, is when I say that what a radian is picture any pizza you want in the world or any pie you want in the world. Now picture a slice of that pie that's as close as it could possibly be to an equilateral triangle, like a slice that is so squat, right? Like not like a long thin slice. That will never be a radian. A long thin slice will always be some small angle, like 11 degrees or something like that. But picture a slice that's as close as it could be to an equilateral triangle, like that's so squat that its base, that the crust is basically as long as the actual edge, right? Now, it's never going to be exact. I mean, it can be exact. It'll never look exact to your eye because the crust is rounded, the arc length is rounded, and the edges are straight. But if you can picture the slice that's as short and squat as possible, so that it almost barely it looks like a rounded equilateral triangle, that's what a radian is. And about 6 of those fit into any circle, no matter how size the circle, no matter how big the circle is. A radian is just a 1/6 of a circle. And why are angles or radians coming up at all? Because an angle, see, if you think of an angle as a section of a circle, then it all starts to make sense, because we're looking at cyclical behavior here. We're looking at motion that happens in cycles. So the best way so we have all this math already worked out for us for the mathematics of a circle. So what we do is we we superimpose the mathematics of a circle onto this physical phenomenon that we're looking at here. Like, we're looking at something that's going back and forth in a straight line. There's no circle or curve to be seen at all. I don't want to make that clear, because this can be very confusing otherwise. We're talking about motion that's going back and forth in a straight line. But we're saying that this motion, with regard to time, can be thought of as cosine function. Cosines and angles are coming in and are appropriate because cosine has that cyclical behavior that you can picture on a graph of up, down, up, down. And cosine is a function that we apply to angles. Don't think of angles as like vertices between, intersecting lines. Of course, that'll throw you off. And don't even think of angles as having to do with curves as such. Think of angles as sections of circles, and realize that we're here trying to chart or analyze and predict cyclical behavior. So omega, angular frequency, the number of radians. So what I'm saying is, okay, what omega is doing that. When we write down x equals x naught cosine omega t, that omega that's measuring radians per second, it's measuring what radians per second have to do with us. If a radian is a 1/6 of a cycle, a radian is a 1/6 of a circle. Think of it in this context as a 1/6 of a cycle. Then what omega, so omega is a rate. It sure is a rate. It's like something per seconds, but it's not meters per second. It's not a distance per time. It's not a speed. It's not a linear velocity. It's what we call, it's not a velocity. It's a frequency. It's a number of times something is happening per second, not amount of distance, but the number of times that something is repeating, that a cycle is repeating. Technically here, omega, if it's measuring in radians per second, it's really, if omega, in other words, if omega is 6 radians per second, what that's really saying in English is that this whole thing is undergoing about 1 complete cycle every second. Omega, strictly speaking, is measuring cycle 6ths. I just spat all over my computer. I'm sure that was, okay. I'll probably electrocute myself now. Omega is measuring, strictly speaking, it is measuring cycle 6ths per second, because the mathematics of that are convenient. The physicality of it is bizarre, but the mathematics, because we already have math, deep math associated with circles, we're trying to borrow the math of circles to describe this physicality of cycles. Okay, so strictly speaking, omega measures cycle 6ths per second, but that's what it's measuring. It's measuring a rate of oscillation, a cycling rate. And we can make it more intuitive if we then say this. Am I doing this right? Yeah. So I'm saying math, we already know something about radians, and a radian is a pure measurement of an angle. And oh, and by the way, I know I wrote this 2 boards ago, but I didn't like emphasize it, right? I mean, the definition of an angle is arc length per radius. Really, in other words, the definition of an angle really is arc length. Like how big of an angle really means like how much of an arc length would it sweep out? But assuming we all cut our arc from a radius of the same size of 1, right? We're just like that. That's so it's radius. So an angle measurement, an angle is an angle is arc length measured in meters divided by radius, which is also measured in meters. So the meters cancel out. Like I know I had this on 2 other boards, but just to be clear, radian is meters divided by meters. So the meters cancel out and you're left with a pure dimensionless thing. Like in other words, radian is not strictly speaking a unit. It's not called the MKS radian system of measurement. It's the MKS system of measurement. Radian is a placeholder. It's a descriptor. And same thing with degree. It's not strictly a unit. It's strictly dimensionless because a radian is just a description of a fraction, a pure ratio. Like how big a chunk of the circle are we talking about? Well, there's 6 of those chunks per full circle. I mean, strictly speaking, there's 2 pi's of them. So if you take your angular frequency as described by the cosine function and divide by, so angular frequency is some rate of radians per second. Divide that by radians per cycle. There's 2 pi radians in every cycle is what I'm saying here. So you're left with cycles per second. Oops, sorry. And this is the thing that's easier to like intuitively picture. Okay, just to try to bring this back to reality now, like, so remember our mass is going back and forth on a spring, back and forth, back and forth. It's not, it's traveling a straight line all the time. And nothing about it immediately seems constant. Like the velocity is not, where it is not constant. How fast it's going is not constant. The rate of acceleration, not constant. What's constant is this patterned behavior. What's constant is its pattern of going back and forth, back and forth. And it's doing so at some rate, some cycling rate. It's doing a number of therebacks per second, a number of round trips per second. Now that is a little bit easier to picture, just like how many times does it go there and back per second. That's called standard frequency. The number of times of any operation that's cyclical is like a cycle could be anything, like a washing machine cycle or a mass on a spring cycle here, or an electronic cycle. A cycle is just, a repeated form, a repeated pattern. And the number of times we do a cycle per second, we call standard frequency, and 1 cycle per second is called 1 hertz, right? So example, like radio stations and stuff. Oh my God. Right. Like NPR or whatever, 93.9 on your FM dial, 93.9 megahertz on your FM dial. Megahertz, mega means million, hertz means this, 1 cycle per second. So when they say 93.9 megahertz, they are saying something in the world, something that we're going to get to by the end of this course, something called electromagnetic radiation. Something in the world is vibrating 93.9 million cycles per second. I mean, that when we say hertz, that's what we mean. Whenever you hear hertz in any context, anywhere in the world, it means something that's going over and over and over again. A hertz is a cycle per second. 93.9 megahertz is 93.9 million repetitions of an electromagnetic pattern, a certain per second. And by the way, that's on your FM dial. FM standing for frequency modulation. Modulation is change. Frequency is frequency. So, okay, so whenever you hear hertz, or in computer processors and stuff like that, when they say, I mean, the number of times it cycles through to perform operations, hertz is a cycle per second. There are 2 pi radians per second for every 1 cycle there is per second. Last way to relate all this together. Okay, okay. So I'm saying, once you have an oscillator, you can't talk about its acceleration or its velocity or all those things are not constant. That all of those things are continuously, smoothly changing. That's the nature of oscillation. Like every derivative you could think of is continuously changing. And you believe that if you believe that cosine is the way to describe an oscillator, because the derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is negative is sine. Sorry, I'm going. And then and back and forth it goes. In other words, you can always take a derivative. You never get to a constant or a zero derivative. So nothing about an oscillator is constant except that fact, if that makes sense. Like everything about an oscillator is always changing, but the way in which it's changing falls into a pattern. And we start measuring the cycles of those patterns, and there's three interchangeably, mutually interchangeable or mutually equivalent ways to talk about the constant cycling rate of an oscillator. You could talk about the omega angular frequency, or you could talk about F, the standard frequency, or what I'm saying here, you can flip that, you can reciprocate that and talk about, as you do in the lab, you could talk about period. Period is the reciprocal of standard frequency. If standard frequency is number of cycles per second, then period is number of seconds per cycle, right? It's all easy peasy once you lay it all out, right? But I mean, it is worth laying all out because it's like not easy peasy when it's not, you get me? So I'm saying 3 different ways that are all mutually, like any one of these, if I'm looking at an oscillator, it's going at some rate, I can identify that rate either by talking about how many radians per second it's doing, or I can divide by 2 pi radians in a cycle and just talk about how many cycles per second it's doing, or I can flip that and talk about how much time each cycle takes. Each one, whether I talk about angular frequency in radians per second or standard frequency in cycles per second, which we call hertz, or if I talk about period, which is seconds, no matter what, I'm giving the exact same information. I don't need at any moment, all I need is one descriptor. But the reason we have all 3 is because 1 is what comes out of the math and is easiest to deal with in the math. 1 comes directly from the math and is directly what we're using, and that's radians per second. And 1 comes directly from measurement and is the most easy to deal with in measurement. And that, well, if I can write this down, sorry. sorry. Okay. Whenever we're picturing an oscillator, the way to identify an oscillator is its cycling rate. Like that's its property, its hallmark, its characteristic is its cycling rate. I'm just here to say any one of three, at any given moment, we have one of three ways to identify a cycling rate, and they're all equivalent. They're all interchangeable. You never need all three at once. But one is what you directly use whenever you're in an experimental data setting, and that's period, T. And one you directly use whenever you're directly in the math and in the analysis, use omega. And the way they translate back and forth to each other is through F, the standard frequency. Okay, so if that helps at all. So one's the more physical way of talking about, one's the more mathematical way, but it's all about the cycling rate. And the thing is, if we now believe, and we're almost, so if we believe all this, and again, all this discussion, it all seems like all this is coming out really of just the fact that we just verified that x equals x cosine, that we verified that x equals x naught cosine omega t, that we verified that that is the description, that is an accurate description of an oscillator. Like once we confirmed that our cosine expression was right and that omega in there was right and meaningful, then now we're off and running. We're saying here on in, from now on, you show me an oscillator and I could tell you just looking at it, I could tell you just looking at it, the rate at which it's going to cycle. In other words, oh, so this is all. Okay, like pages and pages ago in these notes, and I am aware, I see that it's 122. Strangely, we are almost there. I don't know how this happened, but pages and pages ago, I started a numbering list and we were in the middle of number 1. And then I like talked all about all these units and everything. I want to bring, so it was page, so I don't want to end the class by telling you what number 2. I mean, I want to finish this number 1 and just tell you what number 2 is. It's not as long. But the page I'm talking about, in other words, if anybody's lost, I mean, I know I've lost my mind. The page, it was back. Oh yeah, all the way. Oh no, it could have been. Oh my God, are you kidding me? Sorry. The page I'm talking about is, yeah, page 5. Okay. On page 5, we said our finding number one is that from now on in life, if we're walking down in the woods with a mask on and we see a mask going back and forth if we see a mass on a spring of certain M, certain K, what I'm now saying is, okay, we can just look at that thing and say, oh, if I let the mass go from somewhere, it's going to go back and forth at this constant rate of radians per second. And again, and first my brain might go, radians, where's radians in this? But after our whole discussion now, what I'm saying is a radian is just like a sixth of a cycle. So as soon as I see the square root of K over M, I can just say to myself, oh, that's how many cycles it's going to do per second. Technically speaking, I want to multiply that by 6. Divide it by 6 to see how many full cycles it's doing per second. I can do that or not in my, I can do that unit conversion or not in my mind. But just looking at the M and the K, I immediately know how rapidly this thing is going to cycle. Like, okay, that's finding number one. But that's kind of interesting. Okay, now I may have introduced this vocabulary word once, or I may not have, but I'm introducing it right now. So remember, omega. So omega is a square root of K over M. That's our finding number one, is omega is square root of K over M. And I see that it's 125. But now I'm saying, know what K and M are. K and M are constants, yes, but they're a very specific kind of constant that in physics or in science we call a parameter. They are constant for a particular reason. They're not a constant like Planck's constant is a constant or something. They're not a constant of the universe. They are a constant material property of our system. Like K is the stiffness of our spring. M is the heaviness of our object. These are measurements made of our system that we assume will not change throughout the use of our system. Like certain measurements will change, but not these, because these are the materials we're using. Okay, we're just about done. Let me just use this. Hi, thanks. These are the materials that we're using, and we're going to use throughout all the oscillations. We're not going to change the materials. So K and M are constant throughout the motion and the behavior because they are material properties of our system. We call those parameters. Now, why do I care? Because what I'm saying is, and we're just about done, but I'm saying, notice that omega depends on those parameters K and M. It does not, as opposed to depending on X naught. Omega, in X equals X naught cosine omega T, omega is not a function of X naught. Omega is determined. That's a good. It's a Greek.
I want to know.
Okay, I'm totally going to tell you. Good question. I'm totally going to tell you in 1 second. Wait, hold on. Let me just finish 1 second. Omega, the Greek, which is a Greek letter, omega is a function only of the ingredients that we use to make the system. It does not depend on the way we set up the system. Hold on. It's the other class. It's wait, please. Hold on. What I'm saying is whether you pull the mass to here or you pull it to here apparently has no bearing on how rapidly this mass goes back and forth. It will keep time regardless of space. That's huge. That's really our finding number one. I'm saying that it's the minute you look at how heavy the mass is and you look how tight the spring is, you know how tick tock, this clock is going to be. And it doesn't matter whether you set the clock up over here to go tick tock, or you set up to here to go tick tock. If you bring the thing really far away and has a really long way to go in space, it will move much faster, right? Because it has a lot more potential energy, a lot more kinetic energy on average, da, da, da. So if you pull it way back here, even though it has much farther space to go, it will move faster by just enough to take the exact amount of time to get over here as one little guy over here would take to get there. Either short little slow swings, blah, blah, or large fast swings, blah, blah. Either way, the tick-tock rate is the same. That's what we're saying here in finding number one. That's what we mean by harmonic. And find number two, and then we're going to leave on this. Number two is, and this is one sentence, if we believe all the math of what we just did, then that means it's the math that's right. It didn't matter. It didn't even matter whether it was specifically a spring of any stiffness at all. It didn't have to be a metal coil. It didn't have to be a block of wood or whatever. It was any system that obeyed these mathematical relations. So I'm saying now we can generalize, and this is where we're going to end today. I'm just going to write this equation and that's it. We can generalize. We don't even have to have, we don't have to have a K or an M at all. If we have, wait, hold on a second. If we have any, hold on, any variable Z, Z stands for any variable you can conceive of, any dependent variable, any measurement that can be made. Hold on. If you are ever walking in the woods and you come across some Z for which the second time derivative meets this condition, then Z, whatever Z is, and we'll pick up on this on Wednesday, and I'm going to leave and I'm just going to say goodbye without, from here on in, as long as Z it can be expressed in this differential equation here, then Z can measure anything at all. It can measure how far something is from something else. It can measure how far angularly a pendulum bob is from an axis. It can measure the strength of an electric field. It can measure a temperature. Z can measure anything as long as it satisfies this differential equation. And that means Z is oscillating at a rate in time that is constant and independent of configuration, independent of amplitude, independent of initial conditions. Z will oscillate in a cosinusoidal fashion at a rate of omega, no matter how the system is set up. That will be true and so this is the harmonic oscillation phenomenon of all of nature, and that is it. And I am done. And goodbye. I love everybody, including my son who is playing. Goodbye. Have a great afternoon. Thank you guys for your patience. Sorry. Okay. Goodbye. Thank you.